Odontogenesis, or teeth development, is a process that includes the development of deciduous teeth, also called milk teeth or baby teeth, and permanent teeth. Deciduous teeth begin to develop during week 6 to 7 of intrauterine life, whereas development of permanent teeth begins during week 14 of intrauterine life and continues to even up to 5 years after birth. Now, teeth are one of the most diverse organs in humans, both morphologically and functionally. The development of teeth begins around week 6 and from two tissue components, the primitive oral epithelium, derived from ectoderm, and the underlying ectomesenchyme, or dental mesenchyme. The dental mesenchyme derives from craniofacial neural crest cells that migrate from the developing midbrain and the first two rhombomeres into the first branchial arch. Now, the oral epithelium and the dental mesenchyme instructs each other in a sequential and reciprocal way to precisely determine the formation and location of highly specialized teeth, such as incisors, canines, premolars, and molars. The tooth development starts with the thickening of the primitive oral epithelium known as the primary epithelial bands, one on each jaw. Each primary epithelial band soon splits into two, an inner or lingual dental lamina and an outer or buccal vestibular lamina. The vestibular lamina subsequently hollows and forms the vestibule of the mouth, which is the space between the alveolar portion of the jaws, lips, and cheeks. Now, signal proteins such as FGFs, BMPs, and ectodisplaysin cause the cells within the dental lamina to start proliferating and to invaginate in the positions that correspond to the locations of the future teeth. These localized, enlarged projections within the dental lamina are known as the dental placodes. Next, as the dental placodes continue to proliferate, the tooth undergoes morphogenesis, which results in different teeth shapes. This is guided by interactions between epithelial and mesenchymal tissues and progresses through distinct stages defined by morphological features of the dental epithelium, the bud, cap, and bell stages. During the bud stage, the dental placodes proliferate to form a bud-like structure known as the tooth bud that is attached to the oral epithelium by the dental lamina. At this stage, the ectomesenchymal cells start to cluster around the tooth bud, resulting in a condensation of the ectomesenchyme, especially right beneath the bud. And at this point, the tooth bud is made up of two types of cells, an outer layer of low columnar cells and an inner bundle of polygonal cells. Now, the tooth bud is unique in that it has a differential proliferation of cells, which means that different parts of the bud grow at different rates. The cells at the center of the bud proliferate slower than those in the peripheries, leading to the formation of an invagination and turning the bud-shaped enamel organ into a cap shape. This is the start of the cap stage. During this stage, three different types of epithelial cells can be seen, forming the enamel organ, the epithelial part of the tooth germ, the inner enamel epithelium, outer enamel epithelium, and the stellate reticulum. The inner enamel epithelium is a layer of low columnar cells that line the inner surface of the cap's central depression. The outer enamel epithelium is a layer of cuboidal cells that line sides of the cap on the outside. Finally, the stellate reticulum is a bunch of cells that are linked to each other by desmosomes. The stellate cells secrete glycosaminoglycans into the extracellular space. The glycosaminoglycans attract water into the extracellular space, which pushes on the cell membranes of the stellate cells, turning them into the shape of a star. There are also a bunch of non-dividing cells within the enamel organ that sit near the inner enamel epithelium, known as the enamel knots. The enamel knot is a signaling center that regulates the formation of the cusps of the tooth. The number of enamel knots and their location within the enamel organ determine the number and location of cusps in the developing tooth. Now, Now the ectomesenchymal cells surrounding the enamel organ continue to accumulate, especially near the invagination of the cap. The dense condensation of ectomesenchymal cells beneath the cap is called the dental papilla, whereas the accumulation of ectomesenchymal cells that encircle the dental papilla and the enamel organ is known as the dental sac or dental follicle. As the enamel organ continues to grow, the invagination in the cap deepens, forming the cervical loop at the tip of the invaginating epithelium, where the inner and outer enamel epithelium meet. Within the enamel organ, a few epithelial cells between the stellate reticulum and the inner enamel epithelium differentiate into a layer of spindle-shaped cells known as stratum intermedium, and the stellate reticulum start to collapse, reducing the distance between the inner enamel epithelium and the outer enamel epithelium. The tooth germ epithelium then forms the bell-shaped structure that will become the crown of the tooth. The late bell stage is when morphodifferentiation occurs, where the future shape of the crown, such as incisive, canine, premolar, and molar, is determined. It also marks an important stage of histodifferentiation. Histodifferentiation is the conversion of cells of the dental organ into specialized cells, such as amyloblasts, which produce enamel, and odontoblasts, which produce dentin. Following cusp formation, the inner enamel epithelial cells and the dental papilla cells continue differentiating into amyloblasts and odontoblasts, respectively, down the slope of the cusp and up to the cervical loop. Next, as amyloblasts and odontoblasts continue to secrete the mineralized matrix, the dental lamina will disintegrate, which completely detaches the tooth germ from the oral epithelium. Sometimes, when the dental lamina degenerates, it may leave behind nests of epithelial cells called epithelial pearls. These epithelial pearls can give rise to a bunch of abnormalities in the future. For example, supernumerary teeth, odontoma, and eruption cysts. Down below, root formation starts after crown development is underway. The cervical loop cells begin to proliferate downwards to form a two-layered structure known as Hertwig's epithelial root sheath, or HERS. HERS proliferates and migrates downward, guiding root formation, and it also induces the differentiation of odontoblasts forming root dentin. HERS has a limited growth potential, which determines the length of the root. The disintegration of HERS results in the formation of an epithelial network called epithelial rests of molasses, or ERM. This allows the cells of dental follicle to come in contact with root dentin and their differentiation into cementoblasts that deposit cementum on the root surface. The periodontal ligament that connects the tooth to the alveolar bone is formed by fibroblasts differentiating from the dental follicle cells. In addition, the dental follicle gives rise to osteoblasts that form the alveolar bone where the fibers of the periodontal ligament are embedded. These fibers that insert into the cementum and the alveolar bone, providing tooth anchorage, are known as Sharpie's fibers. Permanent teeth develop in a manner similar to that of deciduous teeth, but begins at around week 14 of intrauterine life. The first step in development is the extension of a tiny bit of dental lamina just behind the deciduous tooth bud, called the successional lamina. The successional lamina gives rise to the tooth bud of all the permanent teeth except the molars. The dental lamina in the posterior regions of the jaw bury into the oral epithelium and give off tooth buds that undergo the same stages of development as the deciduous tooth bud. Alright, as a quick recap, teeth begin to develop around week 6 of intrauterine life and can be divided into 3 main morphological stages. After the initiation, the dental lamina forms outpouchings known as dental placodes, which proliferate into enamel organs which change in shape as they grow, starting as the bud, then cap, and finally the bell stage. At the late bell,